So welcome everyone to this talk, which is about the ESP8266 microcontroller and free and open source software. There's a few people filing in. If anybody can shuffle down, might help to make some space. I'll just start with a really quick introduction to myself. My name is Angus Gratton. I used to be a software developer for quite a while. I did sort of back-end software stuff, and I gradually kind of drifted towards doing more hardware and embedded systems projects. I was extremely fortunate. About 5 or 6 years ago, I got hired to be a control systems developer for a small particle accelerator, and that let me really kind of get into doing a lot more in-depth hardware and control systems programming than I'd done before. Since moving to Melbourne 3 years ago, I've been doing sort of bits of hardware design and embedded design, some work with Freetronics, and these days I sort of do general embedded development under the name Red Yak. This talk is about the ESP8266 microcontroller, which is made by a company called Espressive. How many people in the room had heard something about the ESP8266 before this talk? So almost everybody. I guess I should have asked the opposite question. How many people have one? How many people have more than one? More than 10? Okay, we'll have a little support group afterwards, I think. So for the people who aren't familiar with it, the ESP8266 is a microcontroller, so a small computer with I/O connected. It's a 32-bit, 80 megahertz that can be overclocked processor. Uses a somewhat unusual architecture called Extensor, created by a company called Tensilica, and now it's owned by a larger hardware company called Cadence. It's a little bit like ARM if you're used to ARM. The Extensor architecture kind of scales from very small microcontrollers to large computers that run Linux. We're right at the small end here. And like ARM, they don't actually make the chips themselves, but if a company like Espressive wants to make a chip, then they can license the Extensor design for the core they want from Tensilica Cadence and then put it in their chip. So the really useful thing about ESP8266 is that it's got Wi-Fi built in on the chip. You also get quite a lot of RAM of different types and sort of general resources for a chip of this kind. You have some peripherals, sort of general pins you can connect, I/O buses of various kinds, and some low power modes so you can go into sleep. All of that, I guess, is pretty common these days in the 32-bit microcontroller world. It's maybe even a little bit low compared to what you get otherwise. But the real thing you get here is that you pay kind of less than $2 for a single one of these you can buy from China. I put the price in US dollars, not Australian dollars, because the exchange rate keeps changing, and I figured I didn't want to be standing up here saying it's only 10 Australian dollars. So, the structure of this talk, in a quick slide, is I want to talk really quickly about the history of the ESP8266 and how it came to be. A little bit about the benefits and the problems of working with it, because it really is a mixed bag. Then I want to get into the way that the ESP8266 kind of is related to the free and open source software community, and a little bit about some of the reverse engineering efforts that myself and some other people have been part of, and an open source project called ESP-OPEN-RTOS. And then I have a few sort of quick comments about what I think we're going to see in the near future about this stuff, which I think is pretty exciting. So Espressive as a company is based out of Shanghai in China. They were apparently founded around 2008. Their website in around 2010, 2011 had them selling IP for hardware designs, for silicon designs. So this is kind of similar to what I was saying about Cadence and Extensor, is that if you wanted to make a chip, you could license some hardware from them. They had designs. And if you know a bit about hardware and you look at the list on the right-hand side, you can see that there's a lot of things there that you would want if you were going to do something with Wi-Fi. So I guess it's not surprising that a couple of years later they brought out their first chip, the ESP8089, that was announced in 2012, came out in 2013. If you remember back to that time, it was really the heyday of the kind of cheap and cheerful Android tablet that was starting to turn up in supermarkets or like department stores. Most of them weren't very good, but they did hit a very, very low price point. And I think this is essentially what the ESP8089 was targeting. So for example, here's a shot of a main board from an Android tablet around that time. You won't be able to read it, but the bottom right chip is the ESP8089 on a little module along with a Bluetooth chip made by MediaTek. And this sort of just comes in these Android devices. I don't think it went into too many other things. It was mostly Android devices. These days, you actually don't find quite this many silicon vendors or chip vendors on the same board that much with Android stuff. It seems to have gotten really, really heavily integrated. But at this time, especially in the low end, there were lots of people kind of mixing stuff up and selling cheap parts. So the ESP8089, because Wi-Fi is very complicated, actually has a little CPU in it, and that's not uncommon with Wi-Fi devices. They nearly all have a CPU that runs a firmware. So the drivers for this Rock chip kernel, for the board that I just showed, has the firmware directly in the driver, just as a binary. So there's just like a big array of bytes, and it pushes it up to the chip, and then the chip does the Wi-Fi and communicates with the main Linux kernel. This is not how you're supposed to do firmware loading in Linux. There's a whole nice firmware loading mechanism that gets around this problem, but I mean, if you're a sort of quick and dirty hardware company and you just put something out, I guess it works. Whether or not it's a GPL issue kind of depends on your issues or attitude to GPL kernel modules. So that was ESP8089. Late in 2013, the first spec sheets came out for a new chip called ESP8266. At this point, it wasn't well known, even in China, I think. It's certainly not outside of China. The early spec sheets focus on this kind of Wi-Fi interface plus the ability to do a little bit more. So they're trying to sort of branch out of just pure Wi-Fi interfaces. Something else happened around this time, though, which was in 2014, new buzzword came along. Everybody will have heard it, probably heard it way too many times, the Internet of Things. And Espressive sort of heard about it too. They hired a graphic designer who obviously likes stock photography, and they rebranded their website around the Internet of Things. And later that year, the very first ESP8266 modules started hitting the market. So you could buy these from Chinese vendors through websites like AliExpress or Taobao. Quite a lot was sold through Seed, who are sort of the largest and best known open source hardware focused manufacturer seller in China, even though this isn't open source hardware. And at around the same time, the website Hackaday got wind of this and ran a big article about it. This is how I found out about ESP8266. I think it's how a lot of people in the kind of hacker hobbyist community found out that there was this thing called ESP8266. It was a pretty popular article, and they're pretty excited because you could get Wi-Fi for $5. What's not to like, I suppose. Of note, kind of looking at this, the website Zeptobars, which is this great website that takes chips, boils them in acid to get rid of the casing, and then photographs them under a high-power microscope, got hold of an ESP8266, and the silicon itself is still marked ESP8089. The differences are apparently some slight differences in the ROM, and it's a different chip packaging. But it's certainly a case that Espressive were building, obviously, the same IP and finding different uses for it, kind of building it up. So at this point, ESP8266 was being sold as a serial Wi-Fi adapter, and you'd use AT commands to configure it and make it work. The 80s have never left us. The AT commands are alive and well. The depressing thing is when you work with kind of big name modules from kind of bigger vendors, you often find that they love AT commands as well. They just do everything through AT commands. I guess it works, so why fix it? Maybe. And the model there was that you had your main processor, some other microcontroller, and it would be talking to the ESP8266 over serial to say to go onto the Wi-Fi, make an internet connection, do something like that. There was an SDK available from Espressive. Apparently, you had to sign an NDA. You had to convince them that you were a hardware manufacturer who wanted to make lots and lots of these things, and then they'd give you access to some documentation and an SDK. So instead of using AT commands, you could actually program the chip directly. And this is kind of common with a lot of Chinese hardware. There's a model called Gongkai that kind of was a name made up by Bunny Huang to describe what he saw with this stuff. So Bunny's a great open source hardware hacker. If you haven't read his stuff, go and read it. It's excellent. So he was sort of seeing a lot of this kind of sharing of information, data sheets, schematics, sample code, sort of peer-to-peer, but behind closed doors. So certainly in a Western copyright sense, not a legal thing, but if I'm a Chinese engineer and I've got some data sheets from a company that I've signed an NDA with, and maybe you're another Chinese engineer and you've got some data sheets from somewhere that you've gotten from somewhere, we can maybe have a little trade, and you get some information and I get some information and we make some hardware. It's kind of different to just posting it on the Pirate Bay, but it's a sort of one of these grey area things. But it's, according to Bunny, very common in China, and he sees some sort of parallels to the sharing culture in the open source world, even if it's through a totally different mechanism. I recommend checking out a project called Project Fernvale, which was one of Bunny's attempts to kind of take Gongkai hardware and bring it into the kind of open source world by doing sort of clever reverse engineering tricks. The Gongkai approach didn't last very long. About a month after that, publicly leaked virtual machine turned up on the internet with the NDA-only SDK on it. A lot of people got very excited, went and downloaded this. It had a proprietary compiler coming from Extensa that they'd license you. But people still started playing with it, digging around in it. That same month, something called Call Zero ABI support for Extensa landed in GCC. So because Extensa chips ran Linux already, there was largely Extensa support already for the larger chips in GCC, but the way that functions were called varies between the big chips and the small chips, and only that function call support wasn't there. So you could compile code, but you couldn't call any functions. And a Russian developer called Max Filipov, who actually works for Tensilica, landed that support in GCC. It's not clear to me whether that was a Tensilica-funded contribution or a private contribution of his own, because he's been quite involved in the community too. But the sum result was that you could use GCC to work with the Espressive code, although you still had to use a leaked NDA-only virtual machine. Espressive, I think, noticed this though, and they publicly released an SDK. It works with GCC or with the proprietary compiler. Around this time, stuff started happening really fast. A project called NodeMCU appeared in the same month that let you run Lua on the ESP8266. That was originally a closed source project using, I think, the NDA SDK, but after some sort of pressure from the community, they open sourced the Lua interpreter parts, which were mostly other people's open source projects anyway. And this also made quite a few people, I think, sit up and notice that, hey, there's this chip and it's really cheap and it's also pretty powerful. If you can run an interpreted language like Lua, there are a lot of restrictions on what you can do, but the fact that you can do it at all on this budget is pretty impressive. And in the time since then, there's been a port of Python called MicroPython and some stripped down JavaScript frameworks. JavaScript is maybe quite interesting because that's a Samsung project. So, and I believe they've merged support for that platform into their open source JavaScript interpreter. Another thing came out at the end of 2014, which was a second SDK from Espressive that used a real-time operating system. So the first SDK sort of used their own kind of hand-rolled structures for dealing with things like concurrency issues and networking issues. And this SDK was based around the FreeRTOS real-time operating system framework, so you could have tasks and message queues and a few other things, and you could multitask in there. You could also use like a blocking sockets API if you wanted to, which made porting certain kinds of code a lot easier, writing in certain styles a lot easier. And they also released some limited source code at this point. Like up until then, it had just been binary libraries in the SDK with headers if you were lucky. But at this point, at least, the FreeRTOS code, which is under a GPL plus linking exemption license, came out, and some other bits and pieces came out as well. In March of 2014, the last really big development to date happened, I think, which is that an Arduino board support sort of package for the ESP8266 landed. So if you're a hobbyist or an artist or somebody using the Arduino IDE, you could install ESP8266 support and you could run stuff on the Arduino. This is particularly kind of a case of things happening at the right time for the right reasons. The Arduino team recently made it very easy for third-party hardware to be added to the IDE, whereas before then you had to either be official sort of Arduino-supported hardware or you had to sort of do hacks and patches and things never really quite worked very well. Whereas now you put a URL into the Arduino IDE and it downloads everything and it just works. You can start, if you have the Arduino IDE, a recent version, you can start programming on ESP8266 in sort of 10-15 minutes. And the Arduino core support as well just attracted an enormous amount of attention. I think it's a real kind of like open development success story that Ivan, the original developer, posted it on GitHub and a whole lot of people got involved. You can sort of see there are now quite a few very dedicated developers and a lot of people contributing patches. Obviously, the number of contributors is not always a sign of quality, but it is a sign of some amount of level of interest and some amount of momentum. And I think the momentum of this project has been huge. There's a whole lot of extra support in the Arduino core now for doing things that I think the original Arduino team never imagined. And some of Ivan's achievements in sort of shoehorning networking code into something that was never really designed to do networking at more than a very trivial level is really kind of remarkable. And by comparison, so there's been 97 contributors in under a year on the ESP8266 Arduino core. The Arduino core repository's only had 162 contributors to it in that time, which is not, again, not an indication of quality, but it is an indication of enthusiasm, I think, and the attitude of the developers. All of this, of course, despite being open source, is on top of this binary SDK. So there's binary libraries underneath, but there's this whole world of kind of open source stuff appearing on top. Since then, up until now, I think largely it's just been sort of maturity. The SDKs out of Espressive have been fixing a lot of the bugs. They've been adding header files for functions that didn't have header files and other sort of cleanup kind of issues. And the situation now, there's tons and tons of development boards you can get if you want to do an ESP8266 project. These are some that I think are particularly noteworthy. The top two are from SparkFun and Adafruit, who are the largest kind of open source hardware-oriented, hobbyist-oriented American companies. The bottom two are the NodeMCU board and the WeMOS board, which are coming out of small Chinese companies, and they're starting to bring out quite innovative, interesting hardware for hobbyists as well, because they're seeing that there's a market. 3 out of the 4 of these boards, you'll see the metal can on top, which is for sort of containing RF emissions. And those modules actually have FCC test reports filed. As long as you're reasonably sure you're buying from the vendor that filed the test reports, you can be reasonably sure that you're getting something that you could use potentially in a commercial product. So very, very quickly, I just want to walk through some of the sort of common kinds of projects people are building with ESP8266. I could spend all day talking about these, but here's just a few quick ones. And trends. There are lots and lots of lighting projects. You can buy that addressable LED strip for very, very cheaply, where you can make any color you want for each LED. And people are building these into whatever by just attaching them to ESP8266, very cheap programmable lighting controller projects. This one, for example, I think integrates the Philips Hue protocol, so you can control it through their software, or you could. I think they've cracked down on that recently, but that kind of thing. Lots of people building wireless power monitoring projects to do sort of home automation monitoring of power sources in various ways. And there's a lot that kind of just provide kind of like lo-fi DIY versions of really popular commercial IoT products, which I think is kind of fun. Like, this is a DIY Wi-Fi smoke alarm notifier that just uses a microphone to listen to your existing smoke alarm and connect to the internet. And obviously it's not the same product, but it's neat that you can kind of just go and tinker around and build something like that and have it connected to the internet and play around with it. And sort of a quick honorable mention to the project that John Spencer and myself designed that we built on Monday, which was a solar-powered gardening sensor, so for soil moisture, temperature, barometric pressure, humidity, with a lot of extra features kind of bolted on so people could build their own projects out of it with whatever they wanted to do. And we built these, and everybody got them up and connected to the internet on Monday as part of the Open Hardware Miniconf. There's been a few Kickstarter projects sort of building bigger things on the ESP8266, in terms of quantity, that is, sort of more than one-offs. This project was called Moodlight. It was a Kickstarter for a global Twitter mood light that would change color depending on sentiment analysis of Twitter. There's been a few of these kind of Kickstarter scale projects. There haven't been a lot that I know of sort of commercial large-scale projects. The only one I found when I was researching this talk is this direct from China, Chinese market, LED Wi-Fi controller that just has an ESP8266 in it. And somebody bought it and sort of published that. However, I know at least 1 or 2 Western kind of startup companies are developing based on ESP8266 and they're interested in it. So we might see it turning up in sort of consumer hardware maybe in the future. Who knows? Despite all this kind of success and growth, ESP8266 is not without shortcomings. One of them is that there's not a lot of documentation. So even quite simple microcontrollers, the ATmega328P is an 8-bit microcontroller on the most common Arduino boards. It's very simple. You get about a 500-page data sheet and a whole bunch of additional app notes from the manufacturer. The STM32F0, 42, and 72 are the smallest, simplest 32-bit microcontrollers from ST. You get a 1,000-page hardware reference manual plus a whole lot of application notes. ESP8266, you get about 300 pages that covers the hardware, the software, the SDK, everything more or less from the manufacturer. Most of the rest of the information is buried in forum posts and blog posts and questions people ask on IRC and sort of muddle around and figure it out. And as far as I can tell, that's not a difference in language differences. The Chinese language documentation seems to be about the same quantity of documentation. However, not having a lot of documentation is not that uncommon for a lot of kinds of consumer-targeted hardware, the stuff that gets made in really large quantities. Quite often, because if you only have a few customers for your chips, but they're all buying tens of millions of chips, you can afford to just answer their questions as they ask them, or even send an engineer to their site to answer their questions. So I think that's kind of the philosophy that the Espressif people probably came out of in their backgrounds, and they're sort of just letting the community fill in the gap between being able to provide lots of field application engineers to sort of small-scale operation. There's also just weird hardware behavior. This is one example. It's just a little capture on my oscilloscope to illustrate something. The blue trace, it's quite a noisy trace as well, but I think that's the environment I captured it in, not the ESP8266. The blue trace is the reset line on the microcontroller, so when it's down, it's reset. When it comes up, it comes out of reset. The yellow line is just one of the I/O pins. It's GPIO number 2. And GPIO number 2 does 2 weird things when you reset. On the left-hand side, you can't see it on the scope trace, but if it's not allowed to go high at the beginning, you go into a different boot mode, and usually the chip just won't work. And then immediately after that, you get the 26 megahertz like main crystal oscillator comes out there as a clock output. In this case, it happens for a while, and then this was running the Arduino firmware, so it immediately stopped because the Arduino developers turn it off as soon as they can. But it's the kind of thing that will trip you up because most microcontrollers don't have a lot of pins that have strange default functions like this, but ESP8266 has a few. I think this is probably just technical debt from whatever the original applications of the chip were. They haven't had time to sort of clean up the rough edges, but there's more pins like this that have to do a particular thing in a particular way, or you might find out later that your chip doesn't work like it, your hardware doesn't work like it's supposed to. There's a weird default baud rate. Everybody who finds this finds out that by default it communicates at 74,880 BPS. This is not a baud rate I've ever heard of before. What's actually happening here, I kind of figured it out. After going like, what? This is weird. And a lot of people will sort of start up and the SDK will print some stuff at the weird baud rate and then they'll switch to a normal baud rate. So you'll just see sort of garbage for a bit and then normal output. The ESP8266 can run on any crystal speed between 26 and 40 megahertz. It doesn't change the CPU speed, but it changes the multiplier. If you run on a 40 megahertz crystal, you'll get 11,500 BPS, which is a very common baud rate. If you run on the 26 megahertz crystal, you get that proportionally lower, which is 74,880. The weird thing is that everybody uses 26 megahertz crystals. Even Espressive use 26 megahertz crystals in the modules they sell and in their example circuits. I'm not sure why they kind of went with pushing that option, given that it makes this weirdness, but they have. So everybody kind of deals with it. This is a big one for people that are thinking about kind of serious uses for ESP8266. I think a lot of hobbyists kind of just don't care, YOLO, who cares, TLS, right? But the library that they've chosen to use to implement TLS only supports v1.0, which is fully deprecated. Most websites won't accept it these days, or 1.1. It only supports RSA. It only supports relatively short keys that are no longer recommended. I thought that longer keys were now supported, but when I went looking for documentation, I couldn't find any. The documentation still told how to do 1024. So I think kind of if you go off on your own, you might get that to work with longer keys. But it's hard and it's not really supported as far as I can tell. And there are other problems with TLS on the hardware in that you are pushing the limits of what a little microcontroller can do. Although, as I'll sort of get to in a bit, there are other possibilities. So kind of take away from those particular examples, there's more examples, I just didn't want to talk for the whole time about weird hardware, is that if it's not working, look around for undocumented weirdness. Don't assume that it'll behave like the other microcontrollers you've used. I guess questioning your assumptions is good debugging practice anyway, but just do it extra hard this time. So the next part of the talk, I just wanted to talk about the way that free and open source software interacts with the ESP8266. We've already mentioned a few kinds of open source software. There's a GNU-C compiler, obviously, that's enabled a lot of the growth and popularity. There's like a lot of frameworks that are open source that have been ported across to ESP8266, all kind of running on top of a binary-only SDK. The SDK itself uses quite a bit of free and open source software. The TLS library is one called AxTLS that's been around for a while, kind of a lightweight TLS library that's unfortunately not being regularly updated anymore. The IP stack is an embedded IP stack called LWIP that's also quite common. Once you get down below the IP stack in the network layer, there's PS2Mac 8211 and WPA supplicant code, I think taken from BSD releases of those things. There was UDHCP, which is part of the BusyBox project there, as a BusyBox client and server. Some people, including myself, kind of pointed out quietly to Espressive that that was GPL, so they should release source for that, and they kind of removed it in later versions of the SDK and rolled their own DHCP support. Most of these libraries are not exposed to the end users. They've kind of created their own vendor APIs on top. I think if there's one like common thread that I find dealing with a lot of vendor libraries for things, it's creating extra abstraction layers that often aren't any better than the things you had to begin with. But they've kind of wrapped all of this up in their own APIs. I think they've started adding back-in headers so you can get at the functions that they've wrapped because people were complaining. There's almost no source available for these things. Although most of them are BSD licensed, you're supposed to attribute that you're including BSD licensed code as a term, as part of the license in your SDK. There's none of that. You just get the wrapper headers with their copyright notice on it and their licensing. And it's also just frustrating not being able to see the source and see how exactly they're using these. We figured out they're in there just because the libraries still have symbols in them. You can dump out the function names and symbol names and see, obviously, that that's an open source library that's been wrapped up. But it's not clear. There are a few fragments of source code out there. Espressive are doing regular releases of their IP stack separately to the main SDK, they release source. I'm not sure why they do it separately, but they do. And in the real-time OS SDK, the sort of GPL plus exception RTOS parts are out there, and they release the TLS library in that SDK, but not for the other SDK. I don't know why. It's hard to see how these parts integrate, though. They don't build by default as part of the experience. Modifying them may be awkward. They're not done in the way that if you work with open source software, you're used to seeing things work. The initial SDK license was also kind of funny. They've moved away from this now, but I think it's just kind of interesting to point out anyway. If you read this text, it might sound familiar to you. That's because it's the beginning of the GPL version 3. They distributed their initial binary SDK under GPL v3 that had been edited to remove any mention of source. This didn't really make sense, obviously, because if you take out the part, they took out the part about conveying non-source forms, which gives you permission to distribute the binaries, so you didn't have permission to distribute anything. And it's also a violation of the Free Software Foundation's copyright on the GPL. I guess it's easy to poke fun at this stuff. I did think it was kind of funny. After a few people pointed it out, they changed it. I think it's actually kind of a positive sign that, to start with, somebody in Espressive maybe did want to do something like GPL release the source. I kind of feel maybe, it's hard to tell. And then basically management kind of beat them back on various points until they were left with kind of a binary SDK. But I don't think it's an accident that this license turned out to be in there. I think it's a positive sign despite kind of misinterpreting the purposes of it. Whereas the RTOS SDK, which was great, was under an MIT license when it first came out, which was still mostly binary, but at least it's the parts that were source were relicensed under a sort of OSI-approved free software license, which was nice. Later in the year, when they got rid of the GPL hacked-up license, they moved everything to a thing they're calling Espressive MIT, which is MIT with an extra clause that you can only use it on their chips. This is pretty similar to how most hardware companies do their libraries. I don't like it because it no longer meets free software definitions, but pragmatically, it's not terrible. The real problem, pragmatically, is that you mostly have binaries, you don't have actual source code to look at. Although it does make it annoying if you want to integrate parts of that SDK into something else that you want to keep as under a sort of one license or something like that. So all this discussion of binary SDK kind of brings to an obvious question: does the source matter? This is an open source conference, so I suppose people here would probably mostly say yes. But sometimes people sort of think, well, it's close to the hardware, like you can't run it on anything else anyway. Does it really matter? So I'm just going to tell like one short anecdote. This is kind of something that I saw, but I don't really think it's much of an achievement. It's something that anybody who looked would have seen. I was doing some work for John Ox's other company, Superhouse. We're looking at using ESP8266 in sort of commercial hardware and doing a little bit of kind of just due diligence checks. And I sort of noticed that every time I pressed the reset button on a TLS collection or I powered the device up, the sequence of random bytes in the TLS handshake was exactly the same. I think people can probably guess where I'm going from here. So that was in the packet dump. Then I took a raw Wi-Fi frame dump, and the WPA key nonce, which is supposed to be random every time, was repeated in exactly the same fashion. I was like, okay, we don't have an entropy source. There's no source code, so it's not really clear what's happening. It would be nice to be able to just go and look at it, or to audit the source to see things like this. However, I knew that this library was based on the open source AXE-TLS library, so I went and looked at the upstream library. And what you have is a sort of random number generator framework built into there. There's a bunch of clauses at the top for getting entropy any way they can on different platforms, because it's a multi-platform library. At the very bottom, there's kind of a catch-all that just gets like, well, I guess this is kind of random, we'll use that. It takes some stack memory above the current stack address and puts that into an entropy pool, and it takes the address of the stack frame that it's running at. Maybe on a bigger processor, that's not terrible. On an embedded processor, it's pretty predictable, because you get exactly the same thing every time you start it up. And disassembly of that bit of the code kind of confirmed that, yes, that was what was happening. To Espressive's credit, they fixed this. They have a bug bounty if you report bugs to them that they declare legitimate. They pay some money, so they pay me some money. I guess that's okay. When I reported it, I recommended to them that they use random noise from the analog to digital converter somehow. That was my sort of suggestion for what I could think of that would be a good random number source, because random numbers on an entropy, in particular on embedded, is a problem. When they first released it, they used some internal counters in the Wi-Fi hardware, something to do with the Mac that sort of incremented very, very fast. And they didn't seem to me like they seemed pretty unpredictable, but I'm not a cryptographer, I'm not a security person, but I was like, okay, that's obviously better than the same every time. That's a start. But that's where things get kind of interesting, because that part of the anecdote is one thing, but later on, it became evident that the ESP8266 has a hardware random number generator. And this text is not from Espressive documentation. This is from a reverse engineering project that I'll talk about in a minute. And a developer called Alex Stewart, who's very active, just started poking at memory to see if he could find things that seemed to have high entropy content, because we were trying to think of a good entropy source we could use. And he found an address that he could just dump what looked like random whitened data out of. And he ran sort of like the NIST entropy tests on it, and it looked pretty good. And he said, well, what is this if it's not a random number generator? And it turned out Espressive, a couple of releases later in their SDK, had also independently started using this as their random number source, XORed with some noise data out of the analog to digital converter. So well done me for suggesting that. But we hadn't noticed that at the time because the releases were coming out pretty fast. It's kind of a simple example of where if you don't have any documentation and you don't have any source code, there can be really good ways of doing things that the vendor may miss because they're a hardware company doing software, which is traditionally bad, and they're doing it on a budget, they're doing it very fast. They can't catch everything. So that kind of also serves as an introduction to the reverse engineering effort. There's a small but fairly active effort to kind of reverse engineer the SDK and the hardware and figure out exactly what's going on in there. There are a few resources here if people are interested. The slides will be available after the talk, so you don't have to copy these down. There's a wiki with lots of bits and pieces. That's where that quote that I published came from. There are some interesting tools. Alex Stewart, also known as Fugod, has published a really nice, better obj dump, I guess, to do disassembly that looks at some of the metadata left in by the extensor C compiler and uses that to reconstruct the basics of function calls and things like that, because we have symbol information and a little bit of metadata around the libraries. We can actually fairly quickly get to an indication of what the code is supposed to do. There's another project called Scratch-A-Bit, which is probably worth checking out too. I find XTObjdist was more useful for me. Until recently, I was also going to say that the Radare 2, the best known reverse engineering framework that's open source, was adding support for extensor. And then this week on IRC, somebody on IRC called Old Top Man showed me this screenshot, which actually shows, it's probably not readable, but the left-hand side, disassembly of Espressive SDK code, and the right-hand side, a call graph kind of reproduced from that. So those patches are floating around. I don't think they're in the mainline Radare 2 at the moment, but they probably will be soon. And you'll be able to kind of do better reverse engineering with Radare 2 if that's your tool of choice. And I've been focusing my reverse engineering efforts on a project called ESP-OPEN-RTOS, where we started from the last MIT licensed RTOS SDK because we could use it under a sort of easy open source initiative free software license. And we're trying to open source as much of those parts as we can. We've licensed the core project under BSD. We've gone through and found all the places where Espressive did weird things to upstream code in the way that vendors love to do, and we tried to sort of make it so that it's as close to the upstream code as possible so we can merge updates. We're generally just trying to sort of clean things up. This project was originally sponsored by Superhouse as well, which was great. They sponsored the first sort of efforts of development before we sort of changed to a different hardware platform for hardware-related reasons. But it's still going, and it still has contributors. I'm working on it on my own time, other people are working on it. We have upstream-friendly versions of the RTOS SDK, the IP stack. We have an actual libc. For some reason, Espressive decided to create their own kind of libc lookalike that's sort of a libc, but we sort of ripped that out and put in newlib with the nano patches so you could get the behavior you'd expect from a libc. Then we've gone through and basically stripped out, sort of starting from the top down, as much of the binary SDK as we can and started slowly turning it back into source code. This is obviously fairly slow work, but we have sort of configurable C-based startup codes. You can actually control the first thing that the SDK does when it starts up, as opposed to sort of getting handed off from the binary library. And we're at this point where we're mostly open source above the Mac layer. There's a few weird places in the SDK where bits of functionality have gone places that we haven't got to yet, but for the most part, you can do quite a lot from source code. The really nice thing about this as a reverse engineering project is that you don't have to worry about kind of clean room licensing issues for reverse engineering, because we're working from the full software SDK that we're working from is licensed MIT, so we can create derivative works of the binary libraries that are source code and also license those under MIT or relicense them, which saves a lot of the kind of hassles with proprietary reverse engineering. As a very short, quick example, I know it's Friday afternoon, so I don't want to throw a whole lot of source code at you, but a really simple thing. If you want to set a pin on the Espressive SDK, you can use this macro GPO output set, and if you want to set a pin on ESP Open-RTOS, you can use GPO write. Basically equivalent, right? When you get to the implementations, the Espressive SDK has this macro that takes the arguments and generates it into a call to this other output set function, and the implementation of that function is binary, because obviously you wouldn't want people knowing how to set pins on your hardware. And sort of if you read that and you're familiar with C, you'll notice a few weird things. Start with this. It's not sort of input safe. If you put values other than 0 or 1 for bit value, then you'll just get weird behavior that you didn't expect. It doesn't use standard int. They wrote their own version of standard int because I guess they didn't like typing _t. And yeah, it's not documented. There's no comments. That's just how you set a pin. There's the ESP-OPEN-RTOS method. We have sort of what I think are quite readable register access macros in a certain style. It's C99. We use standard int, sort of just basic stuff. It's reasonably type safe. If you pass a value that's out of range, it just does nothing rather than doing unusual side effects. And that's the kind of approach that we've tried to extend to where we're recreating the rest of the SDK. A lot of it at the moment is still at the point of being exact recreations of the binary SDK, but that's sort of an interim point at this point. The other big thing that we have is the embed TLS library. This was originally called Polar SSL. ARM bought it last year, and it used to be dual licensed GPL, but then they Apache licensed it in September. Obviously GPL is a problem even no matter how you feel about GPL, because if you've got binary libraries, you just can't do anything, which is obviously what the GPL wants, but in our case we're sort of trying to do our best with this mishmash. It lets you use modern crypto, yay! You can have long keys, you can have elliptic curve, you can do certificate chain validation, you can do CRLs, all that kind of thing. The codebase is audited, the codebase is actively maintained. That's not the same as saying the codebase is secure, but it's obviously a good start, and we think it's the one to bet on in terms of supporting a TLS library. There are still limitations using it on such a small microcontroller. It uses a lot of RAM. We had to do some clever hacks on the internal side, because before then you couldn't load read-only data byte-wise from flash. You had to write special access code to do word access, so we added a sort of underlined load handler so you could get around that. And there's quite a few kind of other third-party libraries that we're in the process of porting over to ESP-OPEN-RTOS. And because we're hacking into the binary SDK libraries at the moment, we have a kind of fairly horrible build system that pre-processes them to rip out the parts that we've already replaced, and namespaces all of the binary symbols with a prefix so that it's obvious what came out of the libraries. Espressive's solution was usually to rename the thing in the third-party library, whereas we're renaming the stuff in their library so we don't have to touch the third-party libraries. And yeah, we're recreating things in C. Alex Stewart deserves a lot of the credit for that. He's doing really good work. I was hoping to have a kind of automated regression test system to show you in time for this, but the open source hardware miniconf got in the way. Because we're going around recreating and then messing around with undocumented hardware, it's very scary to start changing stuff because you don't know what you're going to break. So designed a small board with 2 ESP8266s and a supervisor microcontroller, and the idea is to be able to have automated tests that push code to both of the ESP8266s, and they interact with each other, and they basically say whether they get the expected result. So you can run it almost anywhere because it sets up its own little networks, and it should show reasonably quickly if we've made obvious regressions when we start actually changing the APIs. And that obviously gives you that slightly more secure feeling that you're hacking away in the dark, but you'll get somewhere. Once that's in place, we've got some more decompiled code sitting in a branch we'd like to merge. I'd actually like we're at the point where we can disassemble all of the binaries and then run them through the assembler as part of the build process and get something that's very, very close to the original binary. Once we close that loop, we can put the disassembled binary libraries in our source tree, which is still horrible, but it lets us kind of add comments and change little bits of it if there's an off by 1 errors and things, or calls to string copy where there shouldn't be any. Somebody mentioned that yesterday in their talk. So we can start to sort of make little changes as we convert it to C code and try to sort of clean it up. So the status of the project is it's definitely in development. It's grown beyond a single person's pet project, which makes me very happy that other people are finding this useful and contributing. But it's still quite an immature project. We have to mature it more. So my little call out to come and help if you're interested in this. If you've done some embedded development, you're interested in really messing around with hardware on C, it's an opportunity to kind of play with something kind of unusual and work with it. We have code of conduct, we have coding standards, how-tos for getting involved. The documentation is a little bit patchy at the moment, but if you find something is not well documented, please just come and tell me and we'll work through it because I want it to be better documented. If all of that sounds a little bit too much like hard work, I don't blame you. It is fairly hard work, although it's rewarding. I would recommend if you just want to play with ESP8266, go and get the Arduino libraries. They're easily the best way to get up and running on ESP8266. And those 2 Chinese development boards that I showed, especially the Node MCU board, which is open source hardware, are good ones to start with. They're cheap, they're plentiful, they have quite clever features in them to work with the ESP8266 hardware. So very quickly, because I'm almost out of time, I wanted to talk a little bit more about how I think this is an indication of something we're going to see more of. Fabless semiconductor manufacturing in China is really exploding. One of the things I like doing is just like going around and finding random Chinese semiconductor websites and looking at whatever kind of chip they specialize in. I think small companies are going to be noticing that Espressif have had a success here with the hobbyist market. And if we're lucky, some of them may have a better attitude to open source than the sort of almost but not quite attitude that I think Espressif had. The big companies are noticing too, but you know. ESP82 is coming. It has 2 cores, it has more RAM, it has more pins, it has Bluetooth, it has hardware crypto acceleration, it has everything. It's currently in private beta testing, and the people who are beta testing it were asked not to talk about it. It uses the real-time operating system SDK with the same licensing as before. A lot of the software support is still TBA, and I noticed that the free RTOS parts of the SDK, there's no source code yet, so they're GPL violating there. Not that they probably care. And I think that this is really interesting and exciting, but I think it took a while for the SDK on the ESP8266 to get to a really usable point. So we're probably about a year out from this being really good, would be my guess, but I don't have any special information to know. Final slide is a takeaway. I saw this quote from Clifford Wolf, who's an awesome hardware hacker who's currently working on doing open source FPGA toolchains, and I just really liked it. He's talking about essentially how manufacturers don't always predict all of the things that are going to be done with their hardware, and the creative people can try other things. And I think this is a great example of that, because I don't think Espressif really would have anticipated how popular the ESP8266 would be with hobbyists. They certainly wouldn't have thought that they'd be the most popular Arduino core with the most growth, kind of beating out solid efforts by companies, big companies like TI or Intel to get into the Arduino space. And a lot of that is enabled by free and open source software, and it's why we should push for more of this stuff to become open. Very quick thanks to Alex Stewart and Ivan, the main Arduino core developer, who have really done really good contributions to this stuff, and Superhouse for sponsoring the initial work that I got to do. Laura Thompson said to put something cute on your final question slide, so this is a picture of my cat supervising ES plant testing.